The northern lights, or Aurora Borealis, and its partner, the southern lights, or Aurora Australis, occur in the atmosphere of the planet Earth. So what's going on here, and why does it happen? Let's start with the magnetosphere. The Earth has a magnetic field around it, and the north and south poles are basically where the magnetosphere enters the Earth. Now, due to the Earth still having a molten outer core, the outer core can move a bit like a very sludgy liquid and can slowly transfer heat out from the hotter inner core to the rest of the planet. As part of the outer core heats up and starts to slowly rise, cooling equally slowly as it does so. As it rises, though, due to the rotation of the Earth, this rising sludge is also subjected to the Coriolis force. So the sludge rotates on its axis. This results in several kinds of upside-down, slow-moving tornadoes deep within the Earth. These tornadoes mainly contain iron and nickel. It's the effect of this motion that actually creates the Earth's magnetic field, as the motion lines up the iron particles in the sludge. And when compared to most of the artificial magnets that humans can create, the magnetic field created by the movement of the outer core is relatively weak. But due to the scale of the source of the magnetic field, the effects of this magnetic field can be felt all over the globe, even reaches out high into the atmosphere and beyond. Now, if you consider the Earth to be one large bar magnet, the lines of the magnetic field curve round from one pole, bulging out in the middle, and curve back down towards the other pole. So these curved lines that a compass is following to point towards the magnetic North Pole. Now, most of this magnetic field is either in the upper atmosphere or even extending well beyond our atmosphere. This field, which is the magnetosphere. Now, the name magnetosphere is slightly misleading. While the magnet part of the name is fairly accurate and obvious, the sphere part is a rather poor description of the shape formed by the magnetosphere. Initially, the magnetosphere around our planet has a rounded shape, especially near the equator. It doesn't sustain that round shape towards the poles. The magnetic field kind of dips down rapidly towards the poles, leaving a shape which looks more like an apple than a sphere. However, this apple shape is also subjected to an external force which alters the shape of the magnetosphere. The Sun is continually producing a stream of charged particles which batter and push against the magnetosphere, causing it to bend and deform. This solar wind contains charged electrons and protons ejected from the Sun, sometimes in large amounts during a coronal mass ejection, sometimes a stream of charged particles is more of a regular, steady stream. This stream of charged particles basically puts a large dent in the magnetosphere on the side facing the Sun, pushing it back down towards the surface of the Earth, resulting in a bow shock on that side of the Earth. On the other side of the Earth leaves a kind of a magnetic tail like a comet stretching out behind the planet, and perhaps like the wake of a boat sailing across the ocean. The magnetosphere is vitally important for the survival of life on Earth, since without it, the charged particles from the solar wind would push at the atmosphere of the Earth, slowly and steadily stripping away all the gas from the planet, leaving behind just a dead planet. As the magnetosphere curves down towards the poles, protection provided the atmosphere is less. So here, the solar wind can strike nitrogen and oxygen in the upper atmosphere. As a result, the wind then ionizes the gases, causing them to glow green, orange, red, or even blue, depending on how much energy the gases have actually absorbed. The gas then releases the energy as photons of light. These patterns are created by the emission of the light, which result in the northern and southern lights. The greater the strength of the solar wind, the more pressure is applied to the magnetosphere, the greater the bow shock pressure, resulting in a low magnetosphere further from the pole, meaning the lights can be seen in locations at a greater distance from the poles. And since we monitor the strength of the solar winds, we can also predict when these unusual locations for the lights are actually going to occur.